Thank you for coming here this morning. So I'm going to talk about a variance reduction approach for stochastic homogenization. And this is a joint work with William Merviel that I'm sure all of you know. The topic we are going to deal with today is related to materials modeled with a random model, such as this kind of material. So this is a picture of a real material. This is not a numerical picture. This is the cut of a composite material used in the aircraft industries, EADS. And you have a composite material here, which is made of a soft material, and orthogonal to the direction of the board, you've got fibers, which are much stiffer than the black part in between. And so because of this fiber, the wing is stiff enough. Okay, and so you have obviously a random locations of these fibers. So maybe the properties of the matrix and the fiber are deterministic, but at least the positions of the fiber are random. And they are random because you decided to, or they are random because you wanted to make a periodic network, but because of the manufacturing process, in the end, it ended up to be random. Okay, so essentially, the materials that you have in the real life have very rarely a random periodic microstructure, and most of the time it is something non-periodic, and for instance something random. Okay, and as I'm going to describe, so what we want to do is to homogenize this material, and so to replace this black and white material by a gray material. And because of randomness, the cost of this is going to be extremely big. Okay, these are very heavy computations, and so we are going to consider from a theoretical viewpoint an equation which is extremely simple, which is the 101 equation in applied mass, which is a minus divergence a grad equation. All right, and all the difficulty will be hidden in the fact that this coefficient here, which models the property of the material, is a random coefficient. I'm going to look at a scalar equation, so this is not exactly mechanics. This is more thermal diffusions or out-of-plane mechanics. Okay, and I've got a matrix A, which is random because of the omega here, and which oscillates at a very small scale, epsilon. So what I'm going to describe is first some background materials on homogenization. Then I'm going to explain the control variate approach, which is the approach I'm going to use. I'm going to describe it in a very general setting. So the control variate approach is essentially based on using a surrogate model, which is an approximate model, which you use to reduce the cost and to improve the efficiency. So we'll need to introduce a surrogate model, an approximate model, and this approximate model is built on the basis of a weakly stochastic model proposed by Arnaud Taramand and Lebris some years ago. So I'm going to describe this model and how we can turn this model to a surrogate model useful for control variance approach. All right, so let's move on random homogenization, and let's look first at the very easy, the easiest case for homogenization, which is not the random homogenization, which is the periodic setting. Okay, it's mostly an academic setting, but it is useful to keep in mind to see the difference between the periodic setting and the random setting. So I'm considering a material, an equation here, minus divergence a grad, with a matrix here which is periodic, which is ZD periodic, and that I'm rescaled at the scale epsilon. Okay. So we know, and this is the classical homogenization theory, that U epsilon is going to converge to the solution. So U epsilon is a highly oscillatory solution, and it converges to U star, which is the solution of that problem here, which is a much easier problem to solve, because here the coefficient, the matrix coefficient A star is constant. So I went from a highly oscillatory coefficient here to a constant coefficient there. And if I have to use finite element here to solve this equation, I will use a finite element of the size of epsilon, the fibers. It will be extremely expensive. And here it's extremely cheap because A star is constant, so I can use any methods with any limited cost. Okay, and this will provide me with a good approximation. So I'm very happy with this equation. Now I need to compute what is the A star, what is the effective coefficient here. And in the periodic case, it's very easy. The effective matrix is given by this formula. So it's an average. A star is an average over the periodic cell. Q is the unit cube. Remember, I'm in a periodic setting. So it's an average of something over the periodic cell. This something is the property of the material times this, where W here is the corrector, is the so-called corrector. Okay, so it solves this equation here. So what I do in practice is that for any vector P of Rd, and I've got D of them, I solve this equation on a unit cell with periodic boundary condition. Okay, so this is not expensive. This is pretty easy. I compute the W here, which is a periodic function. And once I have the W here, I compute that. It's just post-processing. On the unit cell, it gives me the A star, and I'm in business. Okay, with the A star, I've got everything I want. Okay, so homogenization in this periodic setting boils down to solving this equation, which is an equation set on the periodic cell. Okay, so I just have to mesh the periodic cell. So it's pretty easy. In contrast, we'll see that the situation will be completely different for the homogenization, for the random setting. So you need somewhere to average, okay? So you need to have some averaging property, and I'm going to consider properties A, which are random, but such that there is some order in the randomness, okay? Which is the usual assumption. And essentially, if I want to express this in words, it means that the property at one given point of the material and the property at a cell nearby, so if I shift by an integer k, they have the same probability distribution. They have the same law, okay? So if I look at a random material here, okay, the property there and there are different. If I shift by one unit cell, they are different on this realization, but on average, the property there and there are equal, are the same, okay? And under this assumption, you can consider this equation, okay, which is the random equation, where this coefficient here has this property which I call statistically homogeneous. Okay, so it's not periodic, it's not realization per realization, but on average, it has this periodic property. Okay, so I've got a statistically homogeneous coefficient. I look at this equation, and under this setting, the U epsilon, which is the solution to that guy, will converge to the solution of that problem, which is, again, an easy problem because A star is not only constant, but it is also a deterministic coefficient. Okay? And it is essentially deterministic because this is the law of large number. You went from something which is a huge number of random variables to a single deterministic number. Okay? So I'm happy because I have a very simple equation here to solve with a deterministic coefficient A star. Okay, so far so good. But all the catch is how I'm going to compute A star. Okay, remember in the periodic setting, it was easy, I just have to solve on the periodic cell. Now, on the random case, it's a bit more difficult. You remember in the periodic setting, A star was an average over the periodic cell of something. Okay, so again, here A star is an average of the same quantity. Okay, and you need to understand average as average in space and randomness. Okay, so maybe I should write this formula somewhere. So you will have them on the board. In the periodic case, you need to average this, okay? Whereas in the random case, it's exactly the same thing, except that you define average by average over space and randomness. Okay? So this is the statistically homogeneous case. Okay, and now I have to tell you how I define the corrector here. Okay, so the corrector solves the same equation as in the periodic case. Okay, so it's essentially very similar to the equation I started from. It solves the same equation, except now that this equation is set on RD. Okay, I'm not going to comment on the two conditions on the last line. It's not that important. And what is important to keep in mind is that in the random case, this corrector equation is set on the full space, okay, on RD. In contrast, in the periodic case, it was set on the periodic cell. Okay, so if you have to solve a problem, a PDE in the periodic cell here, it's easy. You have to just mesh the unit cube. So, okay, no problem. If you have to solve a problem in RD, it's much more difficult. In even proving theoretically that there is a solution to this equation is not completely straightforward. Okay, but this is what theory tells you. All right. Okay, so in practice, nobody can solve a problem set on RD. So what a standard procedure is a truncation procedure. So instead of solving on RD, what you do is you solve on very large box and you let the size of the box go to plus infinity. Okay? So I consider the same problem here, but now set on Qn, which is an extremely large box, minus n to the d. And in the end, I will send n to plus infinity. Okay? So I consider again the same equation on Qn. And now I need to prescribe some boundary conditions. And for instance, I assume that this W is Qn periodic. Okay? So I replace the W corrector by this guy, which is defined on Qn. And now, from this apparent corrector, I define the apparent homogenized matrix, which is given by this, which is again the average of always the same quantity in space, Qn. Okay? And because you have truncated the stuff, you end up with something which is random. Okay? Essentially, it just amounts to saying that if you have a coin, and if you flip a coin, and you do this an infinite number of times, the probability of having a tail, okay, is 1/2 if you have a fair coin. Okay? Now, if you do this 100 times, and not a plus infinity number of times, the probability of having a tail is on average 1/2, but realization per realization, it is something which is random. Okay? So for the same reason, the guy that I find here on a truncated cell with a finite number of random variables hidden here is a random number. Okay? Okay, so the theory tells you that okay, everything is under control in the sense that if you let the size of the system, the size of Qn go to plus infinity, you converge to the right quantity A star, the reference, the exact homogenized property. All right? But in practice, what you do is you work with your Qn, you have a finite computer, and you are not able to send n to plus infinity, n is equal to 10, and this is with that you have to work. All right? So if I consider here my Qn cell, okay, here is it. And what I consider here is a very academic material. So it is piecewise constant on unit cell. Okay, so you have on each of the unit cell, it is constant and equal to value AK, which can take two values, black and pink, okay, with equal probability. And they are all IIT. Okay, so it's a very simple model. And I do the computation I described you. Here is Qn, here minus n to the 2. Okay, and I do the computation I just said. Okay, so since I'm going to find a random number, what I will do is to do several Monte-Carlo realizations. Okay, so I'm going to draw capital M realizations of this guy, and for each of them, compute the corrector problem and solve for the corrector and assemble the apparent homogenized matrix. Okay, so I do that. I consider several realization AM. I solve for each of these realizations the corrector problem. I evaluate the homogenized matrix. Okay, this is a random number, and now I want the expectation, and just do a Monte-Carlo approach. Okay. And since I've got here IID value, because I started from fields that were IID, not only I have the law of large number, but I also have the central limit theorem that tells me that what I'm looking for, which is the expectation, minus what I can compute, which is this empirical average over several Monte-Carlo realizations. The difference is bounded by something related to the variance. Okay, so I work with probability equal to 95%, and then I've got a confidence interval on this. Okay, so if you do that, here is what you find. As you increase the size of the supercell Qn, okay, you have here the empirical estimator, the central red line, and the confidence interval. Okay, so everything on the far right, on the extreme, on the far right here, will go to A star. Okay, so all these three curves will converge to a single point, which is the homogenized matrix. Very good, but in practice I've got this computer here, and so what I can afford is to work at here 20,000, but not plus infinity. Okay, so all I'm going to address is I fix n. I'm not at n equal to plus infinity. I fix n, and I want to do something for this fix n. Okay, so the idea is that the difference between A star and A star n at omega is made of a systematic error and a statistical error. And the only thing I'm going to address here is how to reduce the statistical error. Okay, so I'm going to completely forget about A star. And what I'm going to focus is computing the expectation of A star n. Okay, and I've got one method, which is the Monte-Carlo method, which provides me with this result. And I want to do something better. Okay, so to do that, I'm going to use a variance reduction approach, which is the control variate approach. Okay, so I'm going to describe now this approach in a general setting. I've got a random variable x of omega, and I want to compute its expectation. Okay, and later on we'll take x is equal to that guy. Okay. So if you want to do this, the first method is the Monte-Carlo method. You draw realizations and you assemble the Monte-Carlo estimate. Okay, so far so good. This is what we have seen. Now I want to describe you a better approach, which is the control variate approach. So it's based on a surrogate model, okay, x approximate, which you will have to choose later on, and all the business is how to pick it. Okay? So suppose I'm given a random variable, which I assume to be close to x in some sense, so it's not completely crazy. And the very important thing is that I assume that its expectation is analytically computable. Okay? So what I'm going to introduce is this c omega, which is x of omega, the variable I'm interested in, minus rho times x minus its expectation. So this is a very important formula. I'm also going to write it on the board. Because this is if you understand this formula, you understand the control variate approach. Okay, so rho here is a deterministic parameter, and I'm going to compute this. I'm going to consider this c. The main thing with this c is that the expectation of c is equal to the expectation of x. Okay, because I have subtracted here the expectation of my approximate model. So the control variate approach boils down to considering this c and running a Monte-Carlo on c. Okay, so what you do is you approximate the expectation of c, which is the expectation of x, by a Monte-Carlo on c. Okay? And so because you do Monte-Carlo on c, you have this classical central limit result where the expectation of c, which is the expectation of x, minus the Monte-Carlo thing, is bounded by something which depends on the variance here of c. Okay? And you gain something if the variance of c is smaller than the variance of x. Okay? So now everything is going to aim at finding rho and x up such that I've got this condition in green, which is the variance of c is smaller than the variance of x. Okay. So the first thing is I'm going to tell you is how to pick rho, because this is the easy thing. Okay. I want c to have the smallest variance as possible. Okay. So if I suppose that I'm given x approximate here, I can compute the variance of c. It's a polynomial of degree 2 in rho. Okay? And what I can do is to pick the rho that minimize the variance of c. Okay, you just have to minimize a polynomial of degree 2 with respect to rho. Okay, so you have an exact formula which is given by this. Okay, so you have the rho optimal given the approximate model there. Okay. In practice, this rho optimal depends on covariance, on variance, and so on that you cannot compute exactly. The only thing you can compute is their empirical mean over realizations. Okay, it's not a big deal. If you do a small error on rho, this is not that a worry. Okay, so we're going to live with this formula, and I'm not going to address anymore this rho in the future because the rho will be given by that formula. Okay, and for this optimal choice of rho, I can compute the gain, which is the ratio of the variance of C divided by the variance of X. Okay, here, and it is something which is smaller than 1. Okay, and it is much smaller than 1 if the correlation between X and X approximate is large. Okay, so if I have a reduced model which is very much related to the model X I'm started with. Okay, so the more correlation there is, the better. Okay, so in the following, I'm going to describe, now I will return to homogenization. The X will be 1 and 3 of the homogenized tensor, okay? And I'm going to describe how I built the approximate model, okay? And next, I will use exactly this formula for that in the setting of homogenization. Okay, so what I'm going to use is a model which was introduced for a completely different purpose, which was introduced to consider rare defects in the periodic structure. Okay, so the idea is very much well explained on this kind of picture. I have a periodic model here, a material with fibers, and it is random because the locations of the fibers are periodic. All the properties are deterministic, and the randomness comes from the fact that you may decide to delete fibers. Okay, so here at random, I decided to delete that fiber and that fiber. Okay, so you have a background material which is a periodic material, A pair. On top of this, you add perturbation, which consists in removing the fiber. Okay, so I've got a deterministic material A pair, which corresponds to these black cells here, where I did nothing. And if I perturb, I go back to this completely white thing here. Okay, and the way I perturbed is by where is it written? This capital BK eta variable. So they are all random. They can take value 1 or 0. If BK is equal to 1, it means that I delete the fiber in the cell K. If BK is equal to 0, I keep the fiber. Okay. So I've got this variable here, which are all random. So I decide independently and randomly whether I delete or not. And it's a rare defect in the sense that I delete very rarely, in the sense that the probability that this guy is equal to 1 is small. It's a eta parameter, which is a small parameter. Okay? So very rarely I decide to remove the fiber. Okay? So here is a picture of the perfect material. Eta is equal to 0. I remove no fiber. And here is a picture of the material where eta is 0.4. Okay, so I almost delete half of the fiber, so that it's not a defect anymore. Okay, and here I presented the stuff on this material with fibers, but this kind of material where I have black and pink things with equal probability, you can also think of that as a defect material in the sense that I've got a background material which is everything is black, and I've got defects which is I put a pink cell instead of a black cell. Okay, and if I do this with probability 1/2, then I have this kind of picture. Okay, now you want to compute the expectation of the homogenized matrix. Okay, and you work on a supercell Qn. So here is the supercell, and if you think of this model, on a given supercell, you've got only a finite number of configurations, because in each of the cells, you have got two possibilities, black or pink. Okay? So you have a finite number of configurations, and so the expectation is just an enumeration. It's a huge sum, okay? But it's not an integral anymore. There are just a finite number of configurations. And what you can do is that in this huge number of configuration, you can consider the configuration with 0 defects, then the configuration was 1 defect, 2 defects, and so on and so forth. Okay? So you can compute the expectation here as the sum over all the realizations with 0 defects times the probability that I have no defect, plus the configuration with 1 defect times the probability I have 1 defect, etc., etc., etc. Okay? And the probability that I have no defect is very easy. So because of the independence, it means that I have no defects nowhere. Okay, so you can evaluate the property. And if I have no defect, then I have a periodic structure, and I've got this tensor A star pair. Okay. If I have 1 defect, then I have got a homogenized tensor here, which corresponds to a structure with 1 defect in the supercell located at the position K. Okay, and the sum continues. Okay. And the probability of having 1 defect is essentially proportional to eta, okay? Because the probability of having 1 defect at 1 cell here is eta. Okay, so what you can do is to expand this expectation as a polynomial in function of eta, where you will see that the leading order term is the periodic thing, because you consider that eta is small, defects are rare, plus corrections due to the fact that I have 1 defect, correction to the fact that I may have 2 defects, and so on and so forth. Okay, so the leading order term is given by this, the periodic situation. Okay, and the first correction is given by that. What I do is I consider a cell with 1 defect. Okay, I solve for the corrector problem for a matrix with 1 defect, and this will give me this contribution here. Okay, so the formula are going to be a bit messy, but I want you to keep in mind the message that the first correction is due to the contribution of configuration with 1 defect. Okay, and because of the periodic boundary condition, if I place this defect here or there, it does not matter. Okay, and the second order correction is due, so the first order is due to the marginal contribution of configuration with a single defect, and now I have the second order corrections, which is due to configuration with 2 defects. Okay, so it's the marginal contribution of a configuration with 2 defects. I can always place the first defect at the center of my cell, and now I have as many configuration as the position of the second defect. Okay, so I do all these computations, which are deterministic computations. Okay, and in the end, I evaluate the expectation. All right. Okay, so now I move back to my original problem. Okay, I want to compute the expectation of E star n, and I am not anymore in a regime where the defects are rare. Okay, if the defects are rare, then I can stop here and we can go all for coffee. Okay, I've got a very nice approach. Now I've got eta, which is not small. Eta is 1/2. The defects are very frequent. And I want to use this model, which is introduced in the regime of rare defect. I want to still use it in the regime where defects are not rare. Okay? So let me describe this on the first order correction. If you understand this, you will have understood everything. What I wrote is that the expectation of A star n is the the contribution of the periodic structure plus the first order correction. And the first order correction is due to the contribution of configuration with 1 defect, and it is scaled by eta because this is essentially the probability of having 1 defect. So what, and this guy is a deterministic guy. This is the marginal contribution of a configuration with 1 defect in the cell. What you can recognize is that this is actually the expectation of a random quantity, which is that one. And that random quantity is the sum over all the positions in the supercell, okay, K. And this is the random variable that tells me I have a defect or I don't have a defect in the cell K. Okay, so this guy is equal to 1 or 0. If it is equal to 0, then I do not add anything. And if it is to 1, okay, I've got a defect in the cell K, then I consider the marginal contribution of that defect. Okay, and I sum over all the cells. So, and I've got this random quantity here, which is built so on the sum over all the cells, taking into account all the contribution of 1 defect. Okay. So the idea is that one. I've got this configuration here. This is the realization of my field. Okay. I have drawn the BK omega, which tells me I've got a defect, I have no defect in each of the cells that are drawn independently. Okay. This determines me the field on the supercell, Qn. From that field, what I can do is to compute the apparent homogenized quantity. Okay, so this is the expensive computation going through the corrector problem and so on and so forth. And what I'm going now to consider is a control variate C, which is the reference quantity I have, okay, minus rho times my approximate model minus its expectation. And the approximate model is what? It is the model I exactly described, where I take into account only contribution of single defects. Okay, so I've got the periodic term plus the first order correction, which is the correction built on the fact that, okay, if I have a defect there, if bk is equal to 1, happens to be equal to 1, I add this to the random thing. Okay, so this is a random model, okay, based on this picture. Okay, I just see whether I've got 0 or 1 here, and if I've got a defect, I take that into contribution. Okay. So what you do not take into account here in this formula is the fact that if I have a configuration with, say, 2 defects, okay, the response with 2 defects is not exactly equal to the response of 1 defect plus 1 defect. Okay, if they are far away, the defect essentially they do not interact because you have got elliptic problems. So the response essentially decreases very fast, and you have 2 bumps at the 2 defects, and indeed it is essentially equal to having 2 completely isolated defects, okay? And then my random model is exact. Now, if I have the 2 defects which are very close, then the bumps will interact somehow, and then I make an error, okay? Okay, so you have this approximate model, and now you run the control variate approach with this approximate model, running so the Monte-Carlo approach on this approximate model, okay? You can do the same for pairs of contributions, okay? So the random model you're going to use is written here, where you take into account whether I've got defects in the cell K and L, and if indeed I've got defects in the 2 cells, then I will consider the marginal contribution here of this pair KL. Okay. Okay. All right. Okay. So now I'm going to describe you on the same example as always, how it works and what is the quality that we obtain. So this is again a very academic material where you pick value, ID value, alpha or beta, I mean gray or pink, with some probability. Okay, so you have got a eta parameter which tells you the relative proportion of pink versus black in the picture. Okay, if eta is equal to 1/2, then I've got equal probability of having black and pink. Okay, and if eta is very small, then I am indeed, or if eta is very close to 1, then I am indeed in a defect configuration where I've got essentially a picture which is essentially black with some pink dots, or vice versa. Okay, so here is the picture that you obtain. So the x-axis is the eta parameter. Okay, so eta is equal to 0, everything is black. This is a deterministic thing. Eta is equal to 1, everything is pink. This is a completely deterministic material. And in between, you have something which is random. The black curves, so the red and the blue curves are the expectation of A star. Okay, so these are the exact results. And the black curves here are the one given by the approach by Anantaraman and Claude, and Anantaraman and Lebris, which is based on the fact, okay, I consider that I have rare defects, and I stop the polynomial expansion at some order. Okay, so you see that these black lines here, which are based on the fact that defects are rare, these black lines are very accurate when eta is small, or if I look at the other situation, they are very accurate here if eta is extremely close to 1. Okay? So if I am indeed in a defect configuration where the defects are rare, then I should not do all this business with Monte-Carlo. I should follow Anantaraman and Lebris and expand and find these black curves, and I am happy. Now there is a regime here which is close to eta is 0.5, where neither of these black curves provides me with a good result. Okay? And if I increase the contrast between the two phases, it will be even more stringent. Okay. So I've got a regime where eta is 1/2, which is I've got equal probability of black and pink. So I have not anymore in a defect configuration, and I cannot rely on their approach. All right. And in this regime where eta is close to 1/2, what I'm going to do is indeed do the control variate approach. Okay. So here is a zoom for the region eta is close to 0.5, and when you do the control variate approach. So the black curve here is, so the y-axis here is the variance of the ratio of variances between the variance of A star n and the variance of my control model. Okay, so if this ratio is large, then it means that I've got a large CPU gain. Okay, because this essentially scales the size of the confidence interval. All right. So if I have eta is close to 0.5, and if I build my approximate model on just the first order corrections, then I've got a gain which is close to 6. And now if I use a better model, which is I not only take into account the contribution of single defects, but I also take into contribution into account the contribution of pairs of defect. Okay, then I end up, look at the blue curve, to something which is a variance reduction ratio which is close to 40. So it means that by using these offline computations and computing beforehand the contribution of pairs of defects, okay, and now using it in the online procedure, in the Monte-Carlo procedure, you end up with a ratio, a decrease in terms of cost, which is equal to 40. Okay, on this example. Okay. All right, and so what is very important for us is that here all the pictures I gave you are pictures computed for some capital N, okay, the size of the supercell. Okay, and I certainly do not want an approach which is very effective in the limit n goes to plus infinity, but which is not effective when n is small. Okay, because all the idea is I work with as n is equal to 10, and I want an approach which is already effective for n is equal to 10. Okay, so here what William did is to plot as a function of n the ratio of efficiency. Okay, and you see, so we computed 3 points. Okay, so this is why these curves are not that smooth. They are 1, 2, 3 points. And what you see is, so this is here the variance reduction when you take contribution of single defects, and here the variance reduction when you take contribution of pairs of defects. Okay, and what you see is essentially these lines are straight lines. So essentially it does not depend on n. Okay, there is a little variation when you move n, but this is not that important. Okay, and so whatever n, the reduction that you have in terms of cost is close to 40. Okay, so it's completely essentially insensitive to the size of the supercell. Okay, if you increase the contrast, so if you make the pink and the black more different, then you have a larger regime where the approximation, the weakly stochastic approximation, does not work, and essentially it works the same. Okay. Okay, so let me skip this. All right. So what I've explained you, I go now to the conclusion. I think it's time to go there. So I try to explain you how we can use a variance reduction approach in the field of stochastic homogenization. Okay, the variance approach, the variance reduction approach we use is a control variate approach. It is an approach which exists and which has been used in many fields of scientific computations. And what we did here is to use it in the stochastic homogenization framework. Okay, for this approach you need a surrogate model, an approximate model, and we built this approximate model on the basis of a model which is based on a rare defect situation, okay, in a weakly stochastic setting. And using this model, you cannot stop at this model. This model does not give you accurate result in the regime where we are, where the defects are not rare, but still you can use it as an approximate model. It's a bit like in linear algebra when you want to invert a matrix. you find preconditioner. Okay, so the inverse of the preconditioner is not a good approximation of the inverse of the matrix, of course. But still, using the preconditioner provides you with a better algorithm in the end. Okay, so it's a bit in the spirit seen from far away is kind of similar. Okay. And okay, so the last comment is that for the moment, computing this surrogate model is a bit too expensive still, because we have to consider all pairs of defects. Okay, and so there are many of them because it's essentially the size of the supercell. Of course, it's a problem which is parameterized by the position of the second defect. Okay, and then you think of reduced basis. Okay. So we want to use reduced basis to do a better job on computing the surrogate model. Okay, here is a list of reference with various contributions. Thank you very much.
Thank you, Frederic. Are there questions? Okay, maybe I start. So, did you try to, a little bit like in the multi-level Monte-Carlo spirit, so did you try to make a box of size 2n and consider that it is 4 times the box of size n, and using the some kind of multi-level idea like that to reduce the variance and get better results?
Yes, we tried this. So the so one thing you can do is to do the multi-level thing, which is to consider growing size and try to compute the expectation on the basis of smaller size. They are less expensive, so you can compute more of them. But the point is that in contrast to, I mean, what I know for the multi-level is that in the end you want to compute something with with a variance. And here, as you increase the n, the variance decreases as well. And so we found out that you cannot have a good trade-off for this reason. Okay. What we tried in a similar spirit is a control variate approach based on the fact, okay, I've got a big supercell, I'm going to cut it into 4. I compute on the 4 little size the thing, and now I built a control model based on this, which is, for instance, the average on this. Okay, and for the moment the results are not that conclusive, but we try this, yes.
Okay, other questions, comments?
Yep.
Let's stop.
In the case when the material is not anymore discrete, in the sense that there is some kind of a checkerboard pattern, and when it's more a random material with some, for instance, some circular inclusions that are distributed with some Poisson distribution. Is there a way to have such a kind of control variate?
So you would like a situation here where the center, say, of the fibers are not anymore on a periodic lattice, but obviously you can use the first order corrections. Okay. Because you just pick one fiber in the material, and because of the periodic boundary condition, it does not matter where you put it. And now the trouble comes when you consider pairs of contribution, because there are infinite number of such configurations. That's a very good question, and one way would be to select a finite number of configurations of pairs, even if we have an infinite number, and do something with this. Okay, so that's we have not tried this yet, and this is yes, something where we would like to go. The same thing is then when you have here, everything is based on the fact that I've got 2 possibilities, okay, black and pink. Now if you have a continuum of possibilities, even for the first order corrections, this is not clear what you have to do. Okay. Because the defects may take, I mean, it's.
And you may have different radius, for instance.
Exactly. So maybe you can do the same, pick some of them and do something with this.